The first thing I want to do is talk about some basic functions and their domains and ranges. So the easiest function I can think of is y equals x. And everybody knows what that looks like. That's just a line going up like that, both directions. The domain is all real numbers, and the range is, of course, all real numbers as well. One step up from that would be y equals x squared, the parabola. Alright, looking like this. The domain is all real, you can put anything in, and the range is y has to be greater than or equal to 0. One step up from that is y is x cubed. And that's looking like this, so it's kind of like this, right? When you cube negative numbers, they become more negative, like that. The domain is all real, and the range is also all real. It hits everything going up and down. And the extensions off of these, like x to the 4th, or x to the 5th, or x to the 6th, all the even ones, they pretty much resemble the same sort of pattern. Like if you do something like x to the 4th, say, it's still going to contain these 3 points, right? 1, 1, minus 1, 1. Only it's going to be bigger over here and less like that. So, but they all have the same basic shape. And similarly for the odd powers, if you raise something up to say x to the 5th or x to the 7th, what you'll generally get is something that looks like this, right? It's like this, they shrink and then they get bigger faster. But they all have the same basic shape, and that's what's important. So what else do we have? Moving on, a couple of other ones. We have y equals absolute x. And that is, of course, the V shape. Alright. The domain is all real. You can take the absolute value of anything, and the range is y has to be greater than or equal to 0. Absolute value can't be negative. Something else we have would be y equals 1 over x. Another basic function. So what's that look like? If you start plugging in some numbers, 1 goes to 1, and 2 goes to 1/2, and 3 goes to 1/3, and so on and so on. So it's going to look like this. The larger x gets, the smaller the whole thing becomes. And the smaller x gets, if we plug in numbers like 1/2, we'll get 2. And if we plug in 1/3, we'll get 3. So it's going to go up like this. The smaller x becomes, the larger the 1 over x is. And the only difference on the other side is it's just a matter of sign. Everything is the same, it's just flipped opposite sign. So when you see 1 over x, that's what you can expect. What else do we have? Y equals square root of x. And that's going to be, that's like the parabola on its side. If the square root of 0 is 0, the square root of 1 is 1. The next number, let's see, it's 2, 3. The square root of 4 is 2. So it's this kind of shape like that. And that's all the even roots sort of look like that, kind of like the parabola resembles, you know. Just as these all kind of look the same, all the even roots look basically the same as well. And if it's an odd root, like the third root, say, you're going to get an additional branch down here. Now, I'm not too worried about the details in these. I just want you to know in general what to expect when we go to graph them. I left out the domain. The domain for this one is, you would say all real numbers but 0. I'm happy with x does not equal 0, can't divide by 0. And the range, you see that the outputs hit every positive value and every negative y value, but 0 is not in there. So you would say the range is everything y does not equal 0. For this one here, if it's an even root, obviously the domain is going to be all non-negatives, and the range is going to be everything from here up. And if it's an odd root, the domain and the range are both all real numbers. That is to say that every number has an odd root. And yeah, you can take the odd root of any number, positive or negative or whatever. That's those. Another one that we have is y equals b to the x, where b is greater than 1. In general, that's going to look like this. All right, if you have like 2 to the x or 3 to the x or something, it's going to grow really fast. If you plug in 0, you get, let's say, for example, we want 2 to the x. 2 to the 0 is 1, 2 to the 1 is 2, and it's going to double each time. 2 squared is 4, and then so it rises real quick. And going the other way, if you plug in negative numbers, you'll get numbers like 2 to the negative 1, which is 1/2. Right? And then 2 to the negative 2, which is 1/4, and then 1/8, and so on and so on. So we call this exponential growth. The domain is all real numbers. You can plug anything into an exponential function. Any number goes, positive, negative, or 0, it doesn't matter. The range, it is important to remember that the range of any exponential has to be positive. It's always y is greater than exclusively 0. You can't get negatives or zeros out of an exponential expression. In the case where b is same thing, if you have y equals b to the x, but b is between 0 and 1, then you're going to have exponential decay. So same kind of deal. The same domain and range. The domain is all reals. Again, because it's exponential, you can plug anything in for x. And the range is, once again, y is greater than 0. So I just want to emphasize that you can't get negatives or 0 out of an exponential expression. What else have... Okay. Another one we have is... the step function, y equals, it's written like that. It's called, it could be called the step function or the greatest integer function, and its description comes in words. When you see this, it means, I'm not going to write it down, I'm just going to say it, but it means, in quotes, the greatest integer that is less than or equal to x. So when you see these double bars around an x, it means the output is going to be the greatest integer that is less than or equal to x. So let's plug some numbers in and see what we got. When you see numbers like, let's say 1. If I plug in 1, what is the greatest integer that is less than or equal to 1? And the answer is 1. So 1 goes to 1. What if I replace that with 2? The greatest integer that is less than or equal to 2 is going to be 2. And the same goes for every integer that you put in. 3, 0, -1, -2, etc., etc. But when you start plugging in numbers like the fractions, if you say the greatest integer of, for example, 1/2, what is the greatest integer that is less than or equal to 1/2? Well, it's going to be 0, so 1/2 goes to 0. What about 1/3? The greatest integer that is less than or equal to 1/3 is also going to be 0. And in fact, any number that is between 0 and 1 the greatest integer that is less than or equal to all of those numbers is going to be 0. So what you get out of this is it's just going to be a flat line for all those numbers, and it's always just going to be 0, 0, 0 until it hits 1, and then it jumps up. And then all numbers between 1 and 2, they get rounded down to 1, right? 1.5, 1.6, 1.7, they all get mapped onto 1. It's sort of like the rounding down function. The reason it's called the step function is because its graph looks like this. Alright, it makes these steps. Now, it's not too important, but it's just something that I think you should know if you see it. So this is what the graph of that looks like. The domain is all real numbers. Right? You can plug anything in here because everything is going to round down to something. But the range is going to be the integers. Range is just the set of the integers. You can't get anything that's not an integer out of this greatest integer function. So we'll do a couple more. Trig functions, say sine x. Alright, so it makes this wavy shape like so. Put the axis in, sine starts here. Alright, the domain of a trig function is, the domain is all real numbers. You can take the sign of any number, and the range is going to be, this upper limit here is 1 and this lower limit is -1 here. So the sine function, if you remember from trig, is trapped between -1 and 1. And that's what that one looks like. If you want to do cosine, it's a similar story. I start out drawing the same sort of thing, only I put the axis in a different spot. The cosine of 0 is 1. And again, the domain is all real numbers, and the range is everything between 1 and -1. Now what we're going to be doing with these is we need to know how to transform them. So I'll get rid of this, and I have a couple of examples there. Let's say that we start out with x squared, and what I want to do is real quick plot the graph of, say, f of x equals x squared plus 2. What's it going to look like? How is it going to change what the graph looks like? And it's at this point that I want to point out that when you see the definition of a function, functions have multiple representations. There's this. You can have a rule that's straight up written out like that, or you can have it in graphical form, or you can see it as a table. All three of these mean the same exact thing. So that's what's going to be important when we go to talk about what's it going to mean to graph something like this. I call this an exterior transformation because it takes the x squared and adds plus 2 to it. Now what is that going to do? Well, it's going to look different first of all because it's going to be written differently, right? X squared plus 2. Now what it does is it takes these previously established output values, these x squared values, and it adds 2 to all of them. So if we go over to our chart here, that's like taking every one of these numbers in the right hand column, in the output column, and adding 2 to all of them. So 0 goes to 2, and 1 goes to 3, and 4 goes to 6, etc., etc. Now, what effect is that going to have on the graph? That's what I want to discuss. Well, since you're taking the original y values and you're adding 2 to all of them, what it's going to appear to do is shift the entire graph up by 2, right? What used to be 0 is now 2. What used to be 1 goes to 3. What used to be 1 is 3. What used to be 4 goes up like this. And the same goes for every one of these points, so that your new graph looks something like that. So what I want you to get out of this is, if you know what the graph of a regular function looks like, and I say, what does it mean to graph that thing plus 2, it's just going to shift the entire thing up by 2 units. Similarly, if I wanted to plot, say, x squared minus 1, it's going to do the same thing, only it's going to take the original values and subtract 1 from all of them. And the effect you're going to get is to shift the entire graph down by 1 unit. That's an exterior transformation. That's the easiest one. So you add something on the end, it's either going to move it up or down as appropriate. The next one I want to talk about is, all right, now I don't have a rule for this function here. We have g of x. I'm telling you that the graph is g of x equals something. That's supposed to be a question mark, but I'm not going to tell you what that something is. It doesn't really matter. We have this representation here, and we have this representation here. What do you get when, alright, so if this is the graph of g of x, what would the graph of, say, 2g of x look like? You'd use the same reasoning that we did over here. It's an exterior transformation. G of x, all these points are already established for you. So we have we have these ordered pairs that are kind of listed here. I can't list them all, right? It goes on for as many as we need. And what this 2 out front does, it takes g of x, multiplies it by 2. So it's going to take all these y values and it's going to double them. So 0 times 2 is 2, and minus 2 times 2 is minus 4, and 0 times 2 is 0. And 0 times 2 is still 0, and this goes to 4. The graphical representation that this is going to have is that it's going to double every one of these y values. Now how do you do that? Well, you do the same thing that we did up in the chart here. 0 goes to 0 because 2 times 0 is 0. 2 times 2 is 4. 2 times 3 is, we go up to, is 6. 2 times minus 2 is minus 4. 2 times 0 is 0. So that the new graph, the transformed graph, if this is g of x, then the graph of 2g of x is going to look like this. It's going to have the same basic shape, only it's going to have the effect of being stretched out a little bit like that. And the same goes if you have any other number out in front. If we did, say, minus g of x. Minus g of x takes all the original y values and multiplies them by minus 1. Now the result that's going to have, I'm going to have to switch up the color here. If we look at the original, minus 1 times 0 is 0. Minus 1 times minus 2 is positive 2. Minus 1 times 0 is 0. So this part's going to look like this. Minus 1 times 2 is minus 2. It's going to be like that. And then minus 1 times 3 is minus 3. So this is the other transformation. If you multiply it by minus 1, it has the effect of flipping it around the y-axis. But I urge you to see this as just a manipulation of the y values. Alright? Again, that's pretty easy to understand because it's an exterior transformation. Those are the easier ones. Now we're going to do something that's a little bit more difficult. We have f of x here, and once again we have all of its representations. We have the numbers written out in a chart, and we have the graph. I want to know, what would the graph of, say, f of x minus 2 look like? F of x minus 2. Now, to understand this, well, you might remember from pre-calculus that whatever you take away on the inside, it's going to show up as a horizontal shift. This should, if you remember, move the entire graph 2 units to the right. But let's see why that is. If we take the, I'll do another example here. I'll show you, if we have, say, g of x equals x squared, we know what that looks like. We plug in 0, we get out 0. 1 goes to 1, minus 1 goes to 1, 2 goes to 4, etc. And it looks like this. So then I ask, what should the g... Alright, now, before we get into the details, I just want to note here. You look at the graph. I ask what numbers map onto 1. What numbers yield 1 as an output? And you'll notice that 1 goes to 1, and minus 1 goes to 1, and 0 goes to 0. Well, what happens when I evaluate g of, say, x, I'll say, plus 4? What's that going to be? Well, if we look at the representation, if g of x is x squared, g of x plus 4 is going to be x plus 4 squared. Now, what's that going to do? Well, I'm going to ask you again, what numbers now are going to get mapped onto 1 and 0? So what number gets mapped onto 1 now? Well, it used to be positive 1, but now it's going to be minus 3 is going to get mapped onto 1. Because check it out, when x is minus 3, you add 4, so you get 1 on the inside, and when you square it, that's going to give you 1 out. The other one is going to be minus 5. When you plug in minus 5 for x, you're going to add 4 to it, get minus 1, square that, that's going to give you 1. and then it's a little bit easier to see that minus 4 is going to give you 0. So if we draw this situation here, what used to go to 1 was minus 1 and 1. But in the new one, what's going to go to 1 is minus 3. So we have 1, 2, minus 3 goes to 1. And minus 5 goes to 1. And minus 4 goes to 0. And so on for every other point on the whole graph. It's going to look like this. Having shifted everything 4 units to the left. It was plus 4, so it went 4 units to the left. The reason being, what I'm trying to get you to see here is that when you add 4 to the inside, x has to be 4 less than it used to have to be to give you the same outputs. So the geometric effect of that is it's going to shift everything this way 4 units, the opposite sign of whatever that is. So when we come back to this one here, we have our graph of f of x. If I want to do f of x minus 2, I know x has to be 2 more than it used to have to be to give me the same outputs. So all I'm going to do to graph that is I'm going to take every point that I know and just shift it over 2 units. So this goes over to here. This goes over to here. This will go to here. This goes to here, and then like so. So that the new graph is going to be like this. Like that. Everything shifts over. Now that's an interior transformation. I call it interior because the modification is on the x. Alright, you're taking 2 away from x first. So it doesn't change what the y values are. It modifies the x values that get mapped onto them ultimately. Alright, so we did, alright, so that's if you do minus 2 on the inside. If I say minus 3, it'll be 3. And alright, another example of an interior transformation is, it looks like something simpler. If we have f of x is this, I want to know what would the graph of f of, say, 2x look like. Now, if you think back to the example that I just did, right, if we start here, we said in this case x has to be 2 more than it used to have to be. So think, what should x have to be now to give you the same result? And I'll give you 2 choices here. Alright, it's either going to be this, it's either going to be that. Alright, it's going to either pull things in by a factor of 2, or it's going to push everything out by a factor of 2. Like so. Right. Which one? So, don't forget this is the original. Which is it going to be? Which makes more sense? Which should f of 2x be? How big does x need to be to give you the same output as the old one? And the answer is, you think about it, it's going to be the blue graph. Because since you're multiplying all the x values by 2, x has to be 1/2 of what it used to have to be to give you the same outputs. And we can show that, for example, if you look at the black one, I'll ask what numbers get mapped onto, if we just have f of x, what x values map onto 0? 0 goes to 0, right? 0, 0, and 3 goes to 0. Alright, well, if you have f of 2x, what does x have to be now? Alright, if you make x 0, you'll get f of 0, and that's still going to be 0, so that won't change. But, since you're multiplying by 2 first, if x is 1.5, that should be the number that gives you 0 out, and because you're going to double it first. And hence, the transformed result is going to be this. So, if you put a big number in by x there, it's going to shrink it. It's going to take the graph and shrink it in by whatever that factor is, which would make this graph, the red graph, since everything is doubled, that would be the graph of f of 1/2 x. Now x has to be twice what it used to have to be to give you the same output. Now that also, you can also take this concept and generalize it to, if I say, alright, if this is g of x, I ask what should g of minus x look like? So you got to think, what does it do? First of all, is it an interior transformation or is it an exterior? It's an interior because the modification is on the x. But what does it do? It's going to switch the sign of the x values that gave you the old outputs. So if I write down a couple of examples here, let's see, -2 gets mapped onto 2, and -3 gets mapped onto 0. And 3 gets mapped onto 1. Alright, that's in g of x. So what's it going to be in g of minus x? Well, since you're taking the opposite sign first, this is going to make 2 map onto 2, and 3 map onto 0, and -3 map on to 1. It's going to take the opposite sign. The geometric effect that is going to have, if we just plot a couple of these, we say 2 goes to 2. Alright, I said 3 went to 0, -3 went to 1, and what are some of the other ones? 0 still goes to 0 because it's unchanged. So what's that going to do? You'll find that it flips the graph around the y-axis. It's a little bit tough to see, so if I just kind of go over it here sloppily. This is what it's going to do. It's going to take the graph and flip it around the y-axis because x has to take the opposite sign of what it used to have to be. So we can do all kinds of things with these graphs. We can move them around. We can shift them and stretch them in any direction that we want. So let's see. Let's apply this to some other graphs. Some concrete ones that we already know how to do. Alright, so if I tell you to graph this, for example, I say graph y equals negative absolute x plus 3 plus 4. What you have to do is recognize this as a basic transformation of absolute x. Absolute x. So what you do is first plot absolute x, plot it lightly, because we're going to be moving it around, and then just apply these transformations in sequence. The first one I'll do is the plus 3. I'll say absolute x, what's going to happen when that goes to absolute x plus 3? Well, we know that it's going to shift it 3 units to the left. So we'll take this graph and go 1, 2, 3, and we'll plot our new one like this. And then what we're going to do is we'll apply the negative. So this is going to go to negative absolute x plus 3. And you know that throwing a negative out in front of a function that's already established is going to flip it down. So it's going to take this new graph and flip it down. And then finally we're going to take that. Let me see if I can center this up a bit. That's going to go to x plus 3 plus 4. So we're going to take that graph and finally add 4 to the outside because it's exterior to this one that's already been established. So what used to be here will now be up at here. What used to be at 0 will now be up at 4. And this is what it's going to look like. So this is the final answer. And that's how you do it without having to, as long as you can, as long as you know what the transformations do, you should be able to just apply them and whip out what the graph is going to look like. Or, I mean, if you're really in a jam, you could just plug in points and work them out all individually, but it's nice to know how to do this quickly. So here's another example of this. I say, plot this. So, alright, what you see is that the original graph is radical x. So I'll just plot that real quick. Alright, 0 goes to 0, 1 goes to 1, 4 goes to 2, and the graph looks something like this. So that's what's going to be transformed. So we just apply these things in sequence. Now you have your pick of which to do first. I'm going to do this -2 first. I'm going to say this goes to radical x minus 2. Now notice, this is accomplished by replacing x with x minus 2. So that's going to push everything 2 units to the right. So that's going to go. So this will go here. This will go here. This one will go here. And we're looking at this now. Alright. And the next thing I'm going to do is add in this 2. So I'm going to take this graph, already established, multiply by 2. And that's going to double all the y values. So 0 stays fixed. Let's switch it up here. 1 goes to 2. 2 goes to 4. So it's going to stretch it out like so. Alright, and then finally, when you subtract 1, it's going to subtract 1 from all these values. So this is going to go. So this, it'll be 2 radical x minus 2 minus 1. So this will go back down to here. This will go to here, and the final graph is going to look something like this. Alright, and that's how it's done. 2 more examples, and then that'll be all. Sometimes you might get caught up looking at something like this, and you think, well, it doesn't follow one of the regular patterns. It's not. You would think it'd be easy if it were x minus 2, but this is 2 minus x. What do you do? Well, you got to play around first. If we just rewrite this as radical, if I factor this negative out, I'll have negative x minus 2, and now it resembles something more like we're used to. Alright, this is something that's comparatively easy to plot, as opposed to this. We don't even need this anymore. Once we rewrite this as this, it's going to be a slightly easier go. But watch how I do this. Again, it's a transformation of radical x. So I plot that once again. So right, 1 goes to 1, 4 goes to 2, so it's like this. And now, what transformations do I have to apply to turn this into this? There's only going to be 2 of them. First step, when you do the interior, when you're looking at interior transformations, you're talking about replacing x with something. Alright? So what I'm going to do from here is I'm going to replace x with minus x, and that's going to go to minus radical minus x. Now what's that going to do? You know from earlier that replacing x with minus x takes the graph and flips it around the y-axis. So far we're looking at this, and now minus 4 goes to 2, and it's like this, and then so this is here. And then to get from this to this, what do? Again, we replace. You're saying x is going to go to x minus 2. Replace x with x minus 2. Whenever you replace the x that way, what it's going to do is shift it 2 units. If you replace x with x minus 2, it's going to shift it 2 units to the right. So once you establish that flip, you move everything 2 units this way. That's like this, and the final result looks like that. So don't be intimidated if you see something like 2 minus x that doesn't exactly fit the mold of what you know. You can definitely still do it. You might have to play around with it a little bit first. Last example that I want to do is I have a t of x here. I'm just going to mess around with it. What I want to do is plot. See, how complicated can I make this? I want to do 2, let's say t of minus 2x plus 1. So it's not too big of a deal as long as we just take these operations in sequence. We'll start out with t of x. Boom, there it is. So the first thing I'm going to do is I'm going to do t of minus x. And what's that going to do? Just like we just did, it's going to take everything and flip it. This might get a little sloppy, but we can do it, right? It's going to flip it around the y-axis, so minus 4, 4, positive 2, 2. That's going to be like this. Alright, so that's this. Now from there, I'm going to replace x with 2x. So what does that do? Replacing x with 2x means x has to be half of what it used to have to be to give you the same output, so it's going to squish it in by a factor of 2. So what used to be 3 will now be 1.5. And what used to be 2 will now be 1. So that's going to look like this. What used to be 2 will now be 1. What used to be 4 will now be 2. So that's going to do it like that. Okay, kind of sloppy, but we can see it. And then from there it's pretty easy, because all that you have to do is multiply by 2, right? 2, t of minus 2x. Exterior transformation, it's going to double every y value. So this is going to, this 3 is going to double up to 6. This minus 2 is going to double to minus 4. And that should be all the points that we need. I'm just going to sketch it lightly, because what I'm going to do is move it. Hope you can see, because the final step is the plus 1. So we're going to take this lightly sketched graph here and just shove everything up by 1. So this, the final spot will be here. This will get put here. What used to be 0 will now go here. This will go here. And this will go up to here. So what that's going to be finally, to start with this, the original graph, and do these 4 transformations. Not so bad. All you got to do is apply everything in sequence, and it's just like that. And that's it.